So right now we're living at an awesome time in uh, astrophysics, in that there's a lot of kind of crazy ideas that are being explored in a serious way. And so the answer is that there are things that can be done to prevent our demise.
What's up, everybody? From Nautilus Magazine, I'm Brian Gallagher, and you're watching Behind the Scenes. Today I'm speaking with Sean Raymond. Sean is an American astrophysicist working at the Bordeaux Astrophysical Laboratory in France. His research focuses on the formation and orbital evolution of planets, both in our solar system and around other stars in the galaxy. His work has been featured in places like Smithsonian Magazine, New Scientist, and others. He also blogs at his website, planetplanet.net. His recent story in Nautilus was a step-by-step guide to our solar system's demise. Sean, thanks for joining us.
It's a pleasure.
So to start off, would you mind summarizing your background intellectually and academically for us?
Sure. So I work basically on trying to figure out how the solar system formed and how other planetary systems form as well. And so in the end, that's taken me down lots of different paths. I've participated in finding planets around other stars, analyzing small bodies like asteroids and comets, building computer simulations of what we think might have happened in the early solar system, and kind of the key processes that shape planetary systems around other stars too. And so kind of a mix of these different things that all fall under a big umbrella of understanding how planets form.
How did you get interested in studying planets and the solar system? What was that initial motivation?
It was just a lucky break. When I was in grad school, I ended up kind of stumbling into this project. It was actually really lucky for me because I was floundering. In grad school, I was on the verge of quitting, doing a project that was not inspiring me. And this other project came up looking at how Earth got its water, and kind of within this realm of how planets form, how the Earth formed. And I jumped into it and I just loved it, and it kind of took me down all these different paths. So it wasn't something I had in my mind from the start. It just kind of luckily kind of came across, and I jumped on the opportunity.
What drew you to science in the first place?
Again, I mean, it was just growing up, I was always into imagination and figuring stuff out. And so in the end, the way those things worked out is I became really into physics and math and computers and stuff. And I've luckily found a way to combine them, doing kind of building these models, which are kind of like telling stories about what we think happened to build planetary systems. It's kind of nice. It's a nice combination of those different pieces.
So, why don't you give us a brief summary of your recent story about the solar system for our viewers who perhaps haven't read it yet?
Sure. So the story looks at the kind of the final days of the solar system. Now, not the final days like measured in Earth days, but kind of looking from now forward, what's going to happen to the solar system. We often think, well, after we're gone, the solar system will still live on for a while, right? And it will for a pretty long time, but not forever. And exactly the steps that are to come is kind of what I looked at in this post. Things like the on Earth, which will happen in about 1 billion years, when we lose our oceans because the sun's getting a little bit every year. Very slowly. We still have 1 billion years, but it's happening. Then on the much longer term, in 5 billion years or so, the sun will become a red giant star, and that will actually engulf Mercury and Venus. Earth is right on the cusp. It might get eaten by the sun, or it might get pushed outward. It's debated. But regardless, Earth, Mercury and Venus are going to get eaten. The other planets' orbits are actually going to expand. The sun is then going to puff off its outer layers, and all that will be left will be a white dwarf. And so the solar system will be kind of this white dwarf sun, maybe Earth, and then Mars, Jupiter, Saturn, Uranus, and Neptune. And then you might think, well, then the solar system will won't look the same, but it'll last forever from then on. And that's what I actually thought until recently. The last piece of the story was only really figured out in the past few years in a paper in 2020. And so then what happens on a longer term is that the sun is still vulnerable to attacks from the outside. And so the solar system itself won't last forever. What will happen is if you wait long enough, another star will pass close enough to disturb the planet's orbits and make them go unstable. And there'll be this process where all the planets will get kicked out of the solar system except for one. And the surviving planet will probably be Jupiter. And it'll survive on kind of this wide, stretched out orbit. And then you wait about 100 billion years longer, and then a star will, statistically speaking, a star will pass close enough to take Jupiter away. And so that's kind of the long story, that at that point, after that happens, there won't be a solar system anymore because the sun will be all alone. So no system to have.
And you've written about, for Nautilus, the phenomenon of rogue planets, planets that are cruising around space without any star. And this is how it happens, right? Where another star will come in and disturb the orbits of planets and strip them away from their main star.
That's one way that we think it happens, yeah. So there's actually a debate right now about exactly where most of the rogue planets that we see come from. And a lot of them probably do form around stars and then are kicked out. So they can get kicked out either by, the system of planets going unstable and basically having this big royal rumble, and one or two or more planets can actually get ejected by strong gravitational kicks from the most massive planets. And those are, the ones that are ejected become rogue free-floating planets. And it's also possible that if planets form kind of far enough away from their stars, then early on, while the stars are still in their birth clusters, another star can pass close enough to kick off the outermost planets and strip them away from their stars, and then they become rogue planets directly.
If I'm not mistaken, most of the exoplanets, planets around other stars besides our sun, are big gas planets like Jupiter, right? Is that because there's this trend, like you point out, that is happening with our solar system, where the last planet will likely be Jupiter? Is that happening in other solar systems in the galaxy?
So most exoplanets that we know are actually much smaller. So the first ones to be found were these, gas giants, just because they're the easiest to find. It turns out they're not at all the most common, though. So the most common are actually much smaller planets, planets between the size of Earth and the size of Neptune or so, planets that we call super Earths or sub-Neptunes, and typically on orbits very close to their stars. And so those are the most common planets we know. The same general process of planets getting kicked out can happen. And it happens, it should be happening in lots of systems, especially systems with gas giants. But actually in those systems that have super Earths or sub-Neptunes close to the star, it's unlikely to eject things. And the reason is because those things are so tied gravitationally to their stars. They're so close in that it takes a big, big amount of energy to free them. And the kind of instability that can, in some cases, kick planets out might instead lead to collisions between planets. And so it's actually very hard to get rid of those very close-in planets. And so overall, as a whole, there are, instabilities are happening. And it's only the ones among gas giants and the ones that are a bit further from their stars that are really contributing to the population of rogue planets. The other kinds of, close-in sub-Neptunes and super Earths, if they go unstable, they just bash into each other.
In the most wild sort of speculative sci-fi technology we might develop, is there any way to prevent this destruction of our solar system that will eventually happen with the sun expanding? Can we do anything to save Earth, or do we just have to reconcile ourselves to the fact that the Earth has a time limit within the solar system?
So right now we're living at an awesome time in astrophysics, in that there's a lot of kind of crazy ideas that are being explored in a serious way. And so the answer is that there are things that can be done to prevent our demise. And so let me give you two examples. One of them is that, the slow brightening of the sun. All right, if we accept that the sun is slowly brightening, well, if the Earth was very slowly moving outward, that could, in theory, compensate for the brightening by keeping Earth at about the same temperature. So how would you going to move Earth's orbit and expand its orbit? There's a really cool paper from about 20 years ago now showing that a single large asteroid placed on a very strategic orbit that basically passed between Earth's orbit out to Jupiter's orbit, and if each flyby was controlled correctly, you'd need to have a close encounter with the Earth about once every 6,000 years that was, the right kind of encounter. And that would gently nudge Earth's orbit outward and basically allow Earth and Jupiter to exchange orbital angular momentum. And so you could do this if we could control this asteroid really precisely, could expand Earth's orbit to maintain the temperature. So that's one example. Another example that would require even, higher, fancier technology would be to very slowly drain material from the sun to slow down its heating up. And there was actually a paper that came out about this in the last couple of days, which is remarkable. And they calculated, if this was possible, what would it do to the evolution of the star? And it would actually prolong the lifetime of the star by quite a bit. And so if we were able to very slowly kind of drain material from the sun, that would both slow down its heating and protect the Earth and make our Earth, habitable for much longer. Of course, to be able to do that is another question, but it is in theory possible.
I mean, what is the sketch of how draining power from the sun would look?
You take, I'm sorry, I said draining mass from the sun. So specifically, you want to just take some of the mass away. And that
Okay.
reduces the pressure to the core, a little bit, which reduces the temperature a little bit, enough to slow down the reaction enough that the net, increase in brightness is compensated.
Was there any proposal about how one might go about draining mass from the sun?
I'm sure someone has started to look into that, but I don't know. I'm not up on that. But I just think it's awesome that people are thinking about these, taking them seriously.
Yeah, definitely. So this piece that we ran in Nautilus was a piece from your blog, and it was actually the last, I think, of a larger series of posts you did about the solar system. What was your reason for writing a series on that now?
Yeah, exactly. That was part of I think a 12-part series that I called the Solar System Story. And I wrote it, I initially sat down and I thought, I'll just write one blog post, kind of summarizing everything I know about how the solar system got there. And I'll use that. That was supposed to be kind of the counterpoint, and then say, well, what could be a little bit different? Let's explore what if things had been a little bit different. And it turned out that I've been working, for my job to try to figure out how the solar system formed for almost 20 years. And so I had more than just one blog post in me to do that. And so I ended up with, writing this out in a decent amount of detail. My goal was to make it detailed enough to really kind of show what I consider all the different interesting aspects, but without making it all technical and boring. That's the goal anyway. And so that's what I threw out there. It was a lot of fun to write, and so now it's complete. And this post about the solar system's demise is the last chapter, of course.
Do you want to share with us how the solar system came to be?
I mean, sure. So the first several chapters are about exactly that, about all the kind of key processes that were involved in forming the solar system. Starting from the disk around the young sun, the birth cluster of stars that the sun was born in, then through to the growth of big bodies within the disk of stuff around the sun, how the Earth formed, why the Earth did not get a lot more massive and end up as a super Earth or a sub Neptune, why Earth has a little bit of water, but not a ton and not no water. Why Jupiter is so massive, and what was Jupiter's role in kind of protecting the Earth or doing something else during its growth. And so I kind of these are the kinds of questions that I explored. And just to give you like a little taste of something sort of specific, one question that I pointed out was that's kind of a paradox, is why do asteroids keep bashing into the Earth? And so why is this a paradox? This is a paradox because people have done these studies for about 30 years showing very clearly how asteroids get to the Earth. What happens is they start off on unstable orbits within the asteroid belt. Their orbits get sort of stretched out such that they're crossing the orbits of other planets. Usually they'll end up crossing the orbits of Mars or something like that. And Mars will kick it inward, and eventually it'll go around for a while and end up bashing into the Earth. Okay? And so that's how asteroids bash into Earth. The problem is those unstable parts in the asteroid belt, those are called the Kirkwood gaps. They're at special places that are called resonances with Jupiter and with other planets. And a whole zillion studies have shown that it's not that hard to clear them out. They're called gaps because they're mostly empty. And so if they're empty, and it takes a tiny fraction of the length of the solar system to empty them out, why do asteroids keep bashing into Earth? We can dig up craters. We can, we have things that are falling onto the Earth. Why does this happen? And so one thing I went into in one blog post, for example, was that question. And the answer to that is that there's other weird effects. There's thermal effects that actually the sunlight bouncing off of asteroids as they spin and re-radiate the light differently acts to change their orbits and push them systematically inward or outward, depending on how they're spinning. And some fraction of asteroids end up getting pushed into these unstable spots. And then they do their thing where they end up bashing into the Earth. And so it's the sun indirectly, it's light from the sun that is causing asteroids to bash into the Earth. And so this is just kind of one interesting thing that I tried to explore within this series of blog posts.
And that must be a really minuscule effect, right? It's just over time, the light shining on an asteroid can alter its trajectory. Because I mean, I would imagine it doesn't feel like that much of a push, right?
Exactly. It's a small effect. It only works, it only operates on relatively small asteroids. It's called the Yarkovsky effect. But it's got this time lever. Wait a billion years and things can happen.
Right. So I had a question for you. I've been watching the show on Apple TV called For All Mankind. Have you heard of it?
No, I don't know it.
Okay. It's like an alternative history where the Soviets landed on the moon first and the space race really ramped up, and both programs of both countries like really went full throttle. And so they have bases on the moon in the 80s, I think, and then they're landing on Mars in the 90s. But there's this one scene that was like really trippy where an astronaut was on the moon and they got caught in a solar flare or solar storm that extended out toward the moon. And since there's no magnetic field or atmosphere, it's really dangerous to be exposed. And what they showed in the scene, kind of rising off the ground and kind of rippling in the air. Is that what would happen? I was really surprised to see that. I was wondering if that was accurate.
Sorry, I missed the last little bit. My connection blipped a little bit. So they saw what rising off the ground?
Moon dust kind of being levitated above the lunar surface. The dust was rising and floating off the ground when the solar storm reached the moon.
That's really interesting. That falls into the very broad category of things I don't know the answer to, but I know who to ask.
Okay.
So I don't know the answer, but it's an interesting thing. I'll have to check that out.
All right. Can you say anything about the impact your piece has had? Have you heard any response from anybody after the piece was published at the end of the solar
I've got
system?
a decent number of people who contact me just kind of appreciating it. I have not gotten feedback telling me that I was wrong, which is nice because I mean I know I did a decent amount of research on it. I was wondering, I'm not sure if there was any obvious offshoots, and so I didn't. Sometimes I get comments from people who have ideas for little offshoots. Well, you explored this path, but what about this? And I haven't heard anyone asking about that. And so there's been feedback, just
Mm,
kind of people. I think especially that last part of the story, when after the sun is a white dwarf, and the solar system at that point doesn't live as long as you would think. It actually lives much shorter than people had previously predicted based on this new study. And so that part of the story is not widely known. So people appreciated just kind of hearing about that part.
okay. What are you working on right now?
I have some, I have just a few random. I mean, blog wise, I have some random ideas I like to explore. The blog is quite fun because I can come up with new ideas and sort of start testing them without having to be super rigorous and dot every I and cross every T and everything. And so I often, in the past several years, I start off new projects sometimes by writing a blog post where I like, hey, here's a new crazy idea. And I sometimes run computer simulations to do little tests of it. And actually I'm doing working on one of those right now, where I wrote this blog post a couple of years ago showing that there's a certain class of orbit that I had never seen. I don't think anyone's really shown to be stable. And so the weird thing about this orbit is basically it's a co-orbital situation. So one planet goes around the star, that's an orbit. Okay? Two planets can actually share the same orbit if they're spaced just right. And so the most common situation like this is called Lagrangian points. And so Jupiter is well known to have these two swarms of asteroids, basically 60 degrees in front of and behind Jupiter's orbit. And they all orbit basically along with Jupiter. So those asteroids are orbiting the sun, sharing the same orbit as Jupiter. So they're kind of co-orbitals. And it's been known for a while that co-orbital planets can exist. So if an Earth were placed 60 degrees in front of Jupiter's orbit and another one 60 degrees behind Jupiter's orbit, and then they were left to do their thing and follow gravity, they would stably orbit the sun. And I've been kind of playing around with a different situation where you can have many planets sharing the same orbit, but they don't have to follow this kind of very, this typical separation of 60 degrees. They can actually end up being a lot closer together, and a bunch of them can share the same orbit. So I've been playing around with that. And that, like I said, that was one that started off as a blog post. And now I'm going to turn into a scientific paper.
Oh, nice. Would you say that the moon shares the same orbit with Earth around the sun, or is that like a different kind of concept?
So in this context, no, it wouldn't be like that. Uh, it would be it would be basically the moon orbits the Earth, and then the Earth orbits the sun. So these are cases where two planets orbit together along the same orbit around their sun. Yeah.
Gotcha. Yeah. All right. Well, Sean, do you want to tell our viewers where they can find you online? We mentioned that you have a great blog, planetplanet.net. Are you also on Twitter or any other social media?
Yeah, I'm on Twitter. My handle is sraymond_astro. So you're welcome to follow me there. I guess that's the main place I go on social media. Otherwise, yeah, like you said, the blog, planetplanet.net.
All right. Well, I'm always looking forward to see what you come up with on there, and it's cool to hear that a lot of your ideas for papers are seeded there. So that's fun.
Hmm.
Well, it was great talking to you, Sean. Thanks so much for joining us.
It was a pleasure. Thanks for having me.